Okay, let's take a look at our Pre-Calculus Chapter 2 Mechanics problems. First thing we're going to be doing is graphing these parabolas, and as we've learned, the key to this, A is 1/2, B is -2, C is -2. We want our x value to be the opposite of B on 2A. Or in this case, we want our x value to be the opposite of -2, 2, on 2 times 1/2, 1. So my little tiny t-chart, x on y, that's 2 on 1. I want this to be 2. Got it right? Now, before I even go there, I could also take a look at this and say, hey, I know this graph is going to go through -2. Because when x is 0, I get that point. I even know it's going to be going down through there. I could even do that much on this. But then I want to put 2 in here, and we'll just do a quick calculation in our head. 2 squared, 4, times 1/2, 2. 2 squared, 4, times 1/2, 2. 2 minus this 2 is 0, so just -2 times 2, -4. Is that all right? So 2, -4 is not just any old point, that's the vertex of this graph. And let's see if we can rectify this over here. Normal parabolas go over 1, up 1, but not this one. This is only half as tall. So it goes over 1, up 1/2, and over 1, up 1/2. Normal old parabolas go over 2 and up 4, but not this one, half as tall. Over 2, up 2. That's pretty reassuring. Over 2, up 2. And normal old parabolas go over 3, up 9, not this one, over 3, up 1, 2, 3, 4 and 1/2. So this parabola, don't make it look like a V down here. It comes out of here flat. It looks more like a U than a V. And so that we'd have a point up here as a target. Good there? Okay. Let's take a look at number 3. So this is in standard form again. I got my x squareds, my x's. So I've got A, I've got B, I've got C. I want the opposite of B, 18, on 2 times A, 2 times -3, -6. So my mini t-chart, I want -3. Now this doesn't help me that this is a -26 because that's way off the chart and going very steep. But I put in -3. Let's go through that one. Let's make sure we're good on this. -3 squared, 9 times -3, -27. -3 times -18, positive 54, and a -26. And I mentioned this the other day. If we write all of those terms out, this first term will always be half the second, and they'll always be opposite signs. So when I combine these, I just get positive 27 minus 26, I get 1. So we are at -3, 1. All right? Normal parabolas, over 1, up 1, not this one, over 1, down 3. Over 1, down 3. Over 1, down 3. Normal parabolas, over 2, up 4, not this one, over 2, down 12. Over 2, down 12 gets me down to here. And that would be all I need, but just for reassurance, normal parabolas, over 3, up 9, not this one, over 3, down 27, and sure enough, I'd hit that -26 if I went down 27 from here. So again, that's a little bit reassuring. Try to make it look like a U at the bottom. Okay? So there are our plain old parabolas. And then we have some with greater than less thans in them. But we're going to start these the same way. We're just going to finish a little bit differently. So again, A is 2, B is -12, C is 20. X is to be the opposite of B, 12, on 2 times A, 2 times 2, 4. So X is 3. Doesn't help to have the 20 on there. Maybe we can come back and take a look at the 20 that would be way up the y-axis. So X is 3. I get 9 times 2, 18, which means this next one better be -36. Double and opposite. I get -12 times 3, -36. Another just place where we can be reassured. Got that? And then plus 20. So when I combine these, I'm just going to get negative 18. Plus 22. So 3, 2 is a point on this graph. I'm just going to put dots, not connecting lines yet. So normal parabola is over 1 up 1, not this one, over 1 up 2. Normal parabola is over 2 up 4, not this one, twice as tall. Over 2 up 8. Over 2 up 8. And just for the sake of comfort, I'm going to be in the right spot. Normal parabola is over 3 up 9, not this one, over 3 up 18, and up 18 from 2 would put me on that 20 for the y-intercept. Then, because this says y is less than, if it was y is equal to, I'd say the points on the curve are all good. Once I put in all the points, it becomes solid. But the points on the curve are almost good. That's where y equals this. That is why we use a dotted line here. It's like an electric fence. You can get close to it, can't touch it. Whereas problem number 7, because y can be equal to, we would still have a solid line there. That's probably the easiest mistake to make, because boy, once we get those points on there, we're just going to be in the habit of drawing the line in. Double check. And then, so where are the good points? These aren't even good. These are just the boundaries. This is keeping my good points either inside of here or outside of here, but better thought of as above or below. This says I want y's that are smaller than, and small y's are down. So any point that's on here, I'm shading beneath this. So you say, well, you shaded outside. Not in my head. I shaded beneath, where the y's are small. You okay there? Any questions? All right. Solve each equation by completing the square. We'll take a look at a couple of these. To complete the square, I want to group my ends, in this case, on one side. I want to leave a blank and get my non-ends on the other side by adding 40 in this case. Then, if there was a non-1 coefficient in front of this n squared, let's say this was 3, I would divide everything by 3, both sides, looking for that 1. Once I've got that, I take this 6 off to the side, I divide it by 2, and I square it. Just a mechanical process. And then I put that result right here. So that gives me 3 squared 9 plus 9. But I did that in red just to emphasize n squared plus 6n was equal to 40. So if I add 9 here, they are no longer equal. So I balance that by adding 9 over there. And that should make this factorable as a perfect square. And it is. That is n plus 3 squared. We can FOIL that and check. I'd get an n times n. I'd get an n times 3 and a 3 times n. So 3n and 3n. And I'd get a 3 times 3. Equals 49. Here's a mistake I've seen a bazillion times before. Show me something I haven't seen. If you're going to make a mistake, make one I haven't seen. I'm tired of this one. Oh, n plus 3 is the square root of 49. It's not the square root of 49. That's half right. It's plus or minus square root of 49. So n is negative 3 plus or minus square root of 49, but that's a nice one. Square root of 49 is just 7. So n is either negative 3 plus 7, 4, or negative 3 minus 7, negative 10. And we probably could have gotten that easier by factoring. But the directions say we're going to solve by completing the square, and that's going to be an important part of a couple of chapters as we move forward, being able to go through that process. Okay. Let's take a look at 18. Same section. So I want to get my k-squareds on one side. And to be honest, I'd rather have positive k-squareds. My choice would be to add 7 k-squareds to get them out of here, but I'd have negative k-squareds over there, or add 8 k-squareds to both sides. I'll do that. Negative 7 k-squareds plus 8 k-squareds gives me a k-squared. So I'm going to add my 9 k's over, plus 17 k's, and I'm going to add my 19 over to here. That all look good? Okay, this one's going to get a little bit uglier, because what do I do next? I have to take this 17 off to the side, divide it by 2, and square it. And 17 squared is 289. So this is plus 289 on 4. We okay there? A little bit uglier. And again, let me back up a second. Reminder, if there was a coefficient, if there was a 2 in front of k-squared, I'd have to divide this before I even start that process. Okay, so I have to balance plus 289 on 4. We okay there? All right, that means this should be a perfect square. It is. That is k plus 17 halves squared. You can check it. I'd get k squared if I FOILed. I'd get 17 halves k's and another 17 halves k's. And 17 times 17, 289, 2 times 2, 4. Equals, let's go to fourths here. So that would be 76 fourths plus 289 fourths. Bit of a mess. So I have k plus 17 on 2 squared equals 76 plus 289, 365 fourths. Does that look right? Okay. So k plus 17 on 2 equals plus or minus, I'm going to do square to top, square to bottom. Square root of 365 on square root of 4, 2. So k is subtract 17 halves plus or minus square root of 365 on 2. And my first hope would be 365 is a perfect square. Is it? It is not. So then I would be responsible for going through and seeing if I can jailbreak anything. And I'd look at it. It's not going to be the most fun one to do. 2 doesn't divide that. Does 3 divide 365? It doesn't. Do we know the trick for 3? 3 plus 6, 9, plus 5, 14. 3 doesn't divide 14. Do we know that trick? Okay, so 4 is not prime, but 5 is, and 5 divides this thing, and 5 goes into this 7 times, 35, and I get 1573. Is that right? 73? Got any good feelings about dividing into 73? You could try 7, but 573, I don't think we're going to be able to break this down. Solution. Okay. Just to emphasize, I want to go back. I'm not going to go through this whole problem, but just to emphasize on this problem right here. When I was starting this, I would group my V's, leave a blank, but before I do anything else, I have to divide by 9. Not just because I can conveniently. If this was a 17 here, I'd have to divide everything by 9. This process will not work without a 1 in front of our lead coefficient. Okay? All right. Factor each. Well, we're going to factor each and solve. If we have 4 terms, 1, 2, 3, 4, our options for factoring become just group them in pairs. But we're going to try to factor out anything individually we can from all 4 first, the greatest common factor. This neighbor has 6 x's to give. This neighbor has 4 x's to give. So far I'm planning on taking x's. This neighbor has a 25, but they don't, but has x's. This neighbor has a 25, but doesn't have any x's. They don't all have anything in common. So I group. I go to these 2 houses and I say, well, that house next door to you had 6 x's to give. You had 4. I guess I'm going to take 4 x's from each of you. X to the 4th. Distributed, I'd need another pair of x's here. Distributed, I'd need a +1 here. If I distribute, I get this. Now I hope I can get another one of these x squared plus 1s here. I don't know if I can. But if I can't match this x squared plus 1, this isn't going to work. How do I get an x squared? I've got to take out a negative 25. Does that work? Minus 25x squared minus 25 equals 0. So I go to this neighbor. They've got 4 x's and they've got one of these things. And my other neighbor has a negative 25. That's no good, but they have one of these things. So I can take one of these things out. Okay. So either x squared equals negative 1, or this guy factors, doesn't it? This factors into x squared plus 5 times x squared minus 5. So either x squared equals negative 1 from there, or x squared equals negative 5 here, or x squared equals 5 there. Well, this one's not troubling at all. How do I get rid of a squared? With not just a square root, plus or minus. X equals plus or minus square root of 5. Now, if we were solving on real numbers, let's take a look at 21's answer here. Number 21's solution. Oh, all they've done is factored here. That's good. We'll just stop there then. That's all they've done is factored. So my factors, and that's fine. If it says factor, it's surprising to me they have plus equals 0 here. So if all they say is factor, our final solution is x squared plus 1 times x squared plus 5 times x squared minus 5. And that is exactly how we will handle it on the quiz then. If it says factor. So I will remind you of that, and I'll just say, just ignore the equals 0. We're not solving anything. Right, questions there? Okay. Another. This might be grouping. I'm not sure. Let's see what's going on here. Oh, this says solve each by factoring. So solve each by factoring. I guess I'm going to group everything on one side because I've got x's here and x's there. I'm going to leave 8x squared. I'm going to add 5x carefully. Negative 17x plus 5, that's a fight. 17 minus 5 is 12x, and the minuses are stronger. If I add 2, I get minus 80 is 0. Now, really a shame that some people right now are probably thinking, well, we're just going to take 8 times negative 80, factors of negative 640 that add up to negative 12. But I can divide out first. I can reduce. 4 divides each of these. So I'm just going to divide both sides by 4. 2x squared minus 3x minus 20 equals 0. So factors of negative 40 that add up to be negative 3. Factors of negative 40 that add up to be negative 3 have to be a negative and positive. Negative 8, positive 5. I put those on 2. And my magic numbers right now are negative 4, got to reduce these, and 5/2. So my factors become x minus 4 and 2x plus 5. Those should equal 0. Any questions there? Therefore, x minus 4 is 0, x equals 4. Or, rescue, subtract 5, divide 2. We okay doing that in one step? I got no problem with it. Notice how these end up being the opposites of my divided magic numbers? Okay. 25, similar, let's group. I'm going to add 2n squared to both sides, 6n squared. I'm going to add 11 n's. I'm going to leave 4 over here, equals 0. I check, 6, 11, 4 can't reduce. Two numbers that multiply to be positive 24 add up to be 11. Popular, just 8 and 3. No, those are different than the last one. Positive 8, positive 3. On 6, on 6. Now, if you do not reduce these, you don't come up with the correct factorization. So I reduce this to 4/3, 1/2. Really, I know my solutions now, don't I? Yeah, my solutions are negative 4/3, negative 1/2, and I have no problem if at that point you do that, but I'm going to go ahead and wrap it up with factors. That would be 3x plus 4 times 2x plus 1 equals 0. X equals, subtract 4, divide 3. X equals, subtract 1, divide 2. All good? Find all zeros. So I believe, let's take a look at solutions 27. I think this is where we start getting some I's in our answers. Is that correct? Yes. Starting at 27, we start getting these weird I's in here. So at this point, and I'll remind you of that when you take it, or when you take the quiz on Thursday, that we're going to have I's in some of these answers. So what is I? You guys have never worked, I'm guessing, with I, imaginary numbers. Is that correct? I squared is defined to be equal to negative 1. We get an I squared, we can turn it into negative 1. It's an imaginary number. But that means that the square root of negative 1 must be I. I is defined to be the square root of negative 1, therefore I squared equals negative 1. Okay, we'll see what that does for us here. All right. First thing, I look for the biggest thing I can tax. 3 and x's. This has a factor of 3 and some x's. This doesn't have a factor of 3, but it has x's. They all have 2 x's I can tax. So I'm going to rewrite this as, oops, that's not what I meant, as x squared times 3x squared plus 9x minus 5. And they are saying here we are to find the zeros. Listen carefully, because this one used to confuse me, and I had 2 questions on this morning. That doesn't mean we put 0 in for x. It means we put 0 in for f of x. This whole side is 0. So just equals 0. Okay, so what have I learned here? I've learned that x could be 0. That's a solution. Now, I'd like to know if this thing factors. Are there factors of negative 15 that add up to be positive 9? Not many choices. 1 and 15 don't work. 3 and 5 don't work, and that's it. So how do I handle this quadratic if it doesn't factor, if only there was some type of formula that would work for us? So, opposite of b, plus or minus square root b squared 81 minus 4 times a 3 times c. It's not 5, it's negative 5. I'll have really, really good calculus students not bother to put the negatives in there. All over 2 times a. All right? So I get Negative 9 plus or minus square root of, let's see, that's 20, that's positive 20, positive 60, 141, all on 6. Is that okay? I think I'm good there. You can check me in calculators if you want to. Those are solutions. Any other solutions? See, these two numbers here make this become 0, either one of them. But what if this number is 0? There's our solutions. I don't think you're going to have any luck breaking 141 down. So, no I's yet. We'll see if we get to deal with some I's here. Number 30. So I get, can't factor anything out. 2 and 11, can't take the numbers out, can't take x's out of everybody. So how do we handle this? Have we dealt with to the fourths before? I mean, if this was x squared and plain old x, it'd be a quadratic, and we could do our factoring thing or our quadratic formula. Well, this is quadratic, but it's quadratic on x squared. If this exponent is double that, and we've got none of the exponents there, we can handle it like that with quadratic formula. But I'm not solving for x, I'm solving for x squared would be equal to the, don't write that down yet, would be equal to the opposite of b plus or minus b squared, etc. But let's check first, see if this thing's factorable. Are there factors of positive 24 that add up to be negative 11? Negative 8, negative 3, right? So this thing factors into, let's put those over 2, get our magic numbers, negative 4 and negative 3 halves. This thing would factor, we'd like to factor this into x, oh, I gave it away. I was just going to put x. We'd like to factor it into x minus 4 times 2x minus 3. But this isn't quadratic on x, it's quadratic on x squared. Is that right? And that equals 0. Does this factor? Perfect square minus perfect square. X plus 2 times x minus 2. This one not so easy. 2x squared minus 3 equals 0. Let's see if we can do this in one step. So x could equal negative 2. That would make this 0. X could equal 2. And let's see if we can do this in one step. From 2x squared minus 3, if it's set equal to 0, who are we rescuing first? 3, using addition. After we rescue the 3, 2 with division. After we rescue the 2, plus or minus square root of, right? And that would be like 90% credit. So x equals negative 2 I like, 2 I like, but this one I'm going to multiply by root 2 on root 2, and I get root 6 all on 2. You guys have done that before. That's right? You guys did that last year, some in geometry. Okay, so again, no I's, but we're going to get to them. Yep. Plus or minus. Thank you. Plus or minus root 6 on 2. Thank you. Okay, this I don't think you've done before. To long divide these. I'm going to set this up just like a division problem. If this said 73 divided by 8, I'd put the 73 under the little division bar and then divide by 8. So I'm going to put x plus 6 out here. I'm going to leave room over the top. I got to have some room to write above this. And I'm going to put negative 8x cubed minus 41x squared plus 32x minus 68. Raise your hand if you've never done a problem like this. Okay, new stuff, so we're going to pay close attention to it. I'm going to do one more after this. I asked myself, how many times does x, what do I have to multiply by x to get negative 8x cubed? I need a negative 8 and 2 more x's, right? I'm not worried about the 6. just making the x go into negative 8x cubed. Since it's negative 8x squared times, I'm going to put the squared over the squared. Negative 8x squared. Kind of like our regular long division with numbers. Now I multiply this by this, and I get negative 8x cubed, right? And I get negative 48x squared. But when I long divide, what do I do with these numbers I put underneath here? We subtract them, right? So I subtract these. I'm going to make these opposites. This cancels, that's why we did it, and I'm left with 7x squared. When we long divide, what do we do in this next step? Bring that down, plus 32x. X, what do I need to multiply by to get 7x squared? Plus 7x. I get 7x squared, and I get 7x times 6 plus 42x. But what do I do with those? Subtract them. And I get, those cancel, they better, that's why we did it, negative 10x minus 68. And I say, how many times does x go into negative 10x? Negative 10 times. And I get negative 10x and minus 60, but subtract those, and I get a remainder of negative 8. So my solution is negative 8x squared plus 7x minus 10. For a while, when you were learning to divide, you got to talk about remainders, but eventually you would have said this was negative 8 over what we're divided by. So this is just minus 8 on x plus 6. Let's try one more of those, and we'll get done as much of this as we can today, and we'll finish tomorrow, and I'm not going to be in a hurry if we need to take more time. Let's go through 34. 3x minus 9 into 3x cubed. Now, just as a side note, if there were no x squareds here, I would put 0x squared. We need to have all the wholes filled, but everything's filled. We've got x squareds, we've got minus 15x's, and a plain old plus 21. I think after seeing a couple of these, you guys are sharp. This isn't going to be a problem. 3x times what? Just x squared. I'm going to put it over the x squareds. That way when I get to here, I know I'm done. So that gives me 3x cubed minus 9x squared. But I'm subtracting those. For a positive 3x squared, bring down the minus 15x. 3x times x plus x gives me x times 3x, 3x squared, x times minus 9, minus 9x. But I'm subtracting. Not going to make that error. Cancels. It should. Negatives win by 6. Bring down a plus 21. 3x times negative 2. Negative 6x, negative 2 times negative 9, positive 18, but I'm subtracting for a final remainder of 3, for a final solution of x squared plus x minus 2, and a plus 3 was left, so plus 3 on what I'm dividing by 3x minus 9. New, but not too bad. Agreed? If you need to review through it, we can certainly have time to go through it. All right, so we're definitely going to be, yes?
Couldn't you simplify the 3 out of 3x?
Oh, that's a good point. X squared plus x minus 2 plus divide everything by 3. Wonderful. 1 on x minus 3. That is definitely a better answer. Thank you. Okay, so we see I from this point on. I's not any old variable. Pretty soon, you're going to learn E's not any old variable. E means something, I means something. So I is our square root of negative 1. I'm going to FOIL this. And I'm going to treat I like it's a variable for right now. And when I FOIL, I get a 1. I get plus 5 i's and plus 5 more i's for a total of plus 10 i's. Is that okay? And then I get plus 5i times plus 5i plus 25i squared. But I squared, we've just learned, is equal to negative 1. So this is right now 1 plus 10i minus 25. So I is an imaginary number, 1 is a real number, 25 is a real number. I can combine my real numbers. 1 minus 25 is negative 24, and I can combine imaginary numbers. That is our final solution, and that is how we should write it. We should always write, this is called a complex number. We should always write those in the form, the real part first, imaginary part second. Okay. So what am I looking for along the way? I'm looking for I squareds. When I take a look at 37, multiply, my very first step, I get negative 20i squared times negative 3 plus 7i. Now, I can distribute this with the I squared, but I don't want to get I to the thirds and to the fourths. I don't want to have to figure that out. Every time I get an I squared, it's negative 1. Multiply through, distribute, negative 60, that's the real part, plus 140 i. I'll give you a quick head start on 38, FOIL. So first 10, outside, negative 8i, inside, negative 15i, last, positive 12i squared. But that guy, here's my little thought bubble, is negative 12. Is that all right? So I've got a real 10 and a real negative 12 for a total of real negative 2. I've got negative 8 and negative 15, negative 23 i's. Hands if you beat me to that answer. Not bad, is it? Now, here's the good news for you. Your calculators have I on it. I is second decimal point. Grab your calculators. Now, with that said, I'm still going to have you show the work on these, but you can check with your calculator. You're still going to have to show the setup. So if we go to our calculator here, and let's clear out here, and I just enter, just as it appears, parentheses, let's see how this works, negative 2 plus 3 second decimal point, close parentheses, times, I think I can just put the parentheses there, negative 5 plus 4 second decimal point, enter. That's handy. Eventually I will free you up for that, but not for this quiz. I need to see that you can get through there by hand. All right? So that's pretty slick. All right. Okay, now, actually I'm going to go through, nope, because I'm doing 44. I'm going to do 44, come back to 42. Now, I's, what do we got? Just a couple minutes? Oh no, we're good. We got 7 minutes. All right. I's are a lot like square roots in that we don't want them in denominators. I don't want an I in the denominator, but I don't mind having negative 10 in the denominator. If I multiply by I on I, what do I get? What do I really end up getting? I get 7i on 10i squared, but 10i squared is negative 10. This would be best answered as just negative 7/10 I. It's just a convention. We just put the I separate from the fraction. Okay? Now, back up to 42, a little bit tougher. So A plus BI is the standard form of these. I think maybe once or twice when we were dealing back in the mechanics for chapter 1, I talked about conjugates. Conjugates from binomials are the same except the sign between them switches. A minus BI is a conjugate of A plus BI. To get this I out of the denominator, this binomial, I want to use the conjugate. So negative 8 stays the same, but then plus 6i on negative 8 plus 6i. What am I really multiplying by? 1. I can do that. Now, before I do that, I probably should have gone ahead and reduced by 2. But since I committed, I'm just going to do my reducing at the end. So distribute here. I get negative 64 plus 48i. So I made the numerator a mess. Over denominator. Let's go through this kind of in our head. Well, first I get a plain old 64. Then I get minus 48 i's, but then I get plus 48 i's. That's the conjugate going to work for us. And then I get minus 36 I squareds. Or negative 64 plus 48 i's on 64 plus 36, right? Or negative 64 plus 48 i's on 100, and now I got to pay the price, I got to reduce. Absolutely no doubt about it, these guys can reduce by 4 for sure. So I get negative 16, I'm going to put it on the 25, and I'm going to put by 4 plus 12 on 25i. Is that okay? All right, 45, binomial in the numerator, binomial in the denominator. I don't care about the numerator. I got to get rid of that I in the denominator. Try this guy. And we'll stop there and pick it up there tomorrow. And if we got to back things up, I'm not going to rush through this. Try the foiling, simplifying here. Did we all arrive at 3 minus 12i plus I minus 4i squared numerator? Okay, the minus 4i squared is a plus 4. 3 plus 4, 7. Minus 12i plus I minus 11i. The denominator, 1 minus 16i squared, but minus 16i squared is plus 16. Now, I would probably accept this at this point, but the better solution is put the real parts together, 7 on 17, minus 11 on 17i. Hands if you beat me to that very, very final answer with those split. All right, how about hands if you made it to there, 7 minus 11i on 17. I'm good with that, but ultimately, that's a real target for us. So I'm going to stop at that point, and we will pick up some other examples tomorrow. I thought that might be pushing it, but I haven't done that before. I still feel pretty comfortable that Thursday can be quiz day, but I'll pick up and do a few of the examples that I still had remaining. That video will be added on for tonight. If there's something there you want to go back over, and the other video, I might get to add it, but I might just do it the same way in class tomorrow, because I got to be adding calculus videos as well today. For quadratic formula, the opposite of b plus or minus square root of b squared minus 4ac all over 2k.
When it's just final zeros, I found like this, which would have been plus or minus 30, negative 30. So
Right. Therefore, x, this is one we're going to have to talk about. Plus or minus square root of negative 3 is
plus or minus 3i. Okay, I was wondering.
Yes, that's something.
Got it.
I didn't hit one like that today. We're going to have to look at that tomorrow. So check your solutions. You're going to see some I's in some answers and see if you can figure that out. We'll talk about it tomorrow.
Oh, it does happen.
Yeah, and we always just assume we're working with real numbers. So what the directions really should say is solve over the complex set of numbers. That means, okay, now we can deal with negative square roots. Negative square roots actually have applications in electronics. That was always my thought, is what in the world do we need imaginary numbers for, just so we can get answers? There's actually electronic applications.